You ever look up at the sky and just wonder about clouds? It seems so simple, right? But here's the thing. The air all around us doesn't actually want to go up. It prefers to stay right where it is. So today, we're going to uncover the 4 powerful, invisible forces that have to physically shove air upwards to create everything from a tiny wisp of a cloud to a giant thunderstorm. I mean, really, stop and think about that for a second. We are talking about millions, sometimes billions, of tons of water just floating miles above our heads. It's an incredible feat of nature, really. And it all has to start with a push upwards. But as you're about to see, that initial push is way more complicated than you might think. And here it is, the core of the whole puzzle. Air is naturally stable. It's heavy. It likes staying close to the ground. So for a cloud to even begin to exist, some outside force has to come along and literally force that air up against its will. So what are these mysterious forces? How does this heavy lifting actually happen? Well, it turns out there are 4 main ways, 4 distinct mechanisms that get the job done, creating the weather we see and feel every single day. Let's get into them. First up is the one that's probably the easiest to picture in your head. It's called orographic lifting. And this is basically what happens when the landscape itself decides to take charge. Now, that name, orographic, sounds a little technical, I know, but it's really simple. Oros is just the Greek word for mountain. So this is mountain lifting. That's it. You've got a bunch of air moving along, and bam, it runs into a mountain. It can't go through it, so its only choice is to go up and over. So as that moist air gets forced up one side of the mountain, we call that the windward side, it gets higher and colder. And that cooling is the key. It squeezes the water vapor out, turning it into clouds and then rain or snow. But then after it crosses the peak, that now dry air sinks down the other side, the leeward side. As it sinks, it warms up, creating a much, much drier climate. This whole process creates a really dramatic effect called a rain shadow. The mountain literally casts a shadow of dryness behind it. This isn't just some small local thing. The Sierra Nevada mountains in California, they're the reason the Great Basin Desert exists right next door. The very same thing explains massive deserts like the Gobi in Asia and the Patagonian Desert in South America. It's all because of mountains. Okay, that makes sense when there's a giant mountain in the way. But what about places that are completely flat, like the plains across the middle of the US? Well, that brings us to our second force, frontal wedging. In this case, the barrier isn't made of rock, it's made of other air. Here's the most important thing to remember. Cold air is dense and heavy. Warm air is light and, well, less dense. So when a cold air mass and a warm air mass run into each other, they don't just mix together nicely. Nope. The heavy cold air hugs the ground, and the lighter warm air gets pushed up and over the top. It's almost like an atmospheric bulldozer. That cool, dense air acts like a wedge, sliding under the warm air and forcing it to rise. And that line where they collide, the boundary, that is the front you always hear the weather person talking about, a cold front or a warm front. These fronts are the reason for a huge amount of the storms and rain we get. So let's just pause for a second and see the difference. With orographic lifting, the barrier is physical, a mountain. It's not going anywhere, it's predictable. But with frontal wedging, the barrier is atmospheric, another mass of air. It's a dynamic, moving battle. One is a landmark, the other is a weather event in motion. But both get the same job done, forcing air to rise. Okay, so we've got a physical barrier and an air barrier. But what if there's no barrier at all? Our third mechanism, called convergence, is what happens when you just get an atmospheric traffic jam. So just picture air flowing in from opposite directions. When it all meets in the middle, it can't go down into the ground, obviously, so there's only one direction left to go, and that's up. It's just a pile-up that results in a huge vertical lift. A good way to think about it is like a huge crowd trying to funnel through one small exit after a concert. People just get squeezed and pile up. Well, with air, it's pretty similar, but with that one big difference. When the horizontal flows collide, they get squeezed upwards. All that congestion forces a really powerful lift. And you know, there is no better real-world example of this than Florida. Just about every day, you have sea breezes blowing in from the Atlantic on one side and from the Gulf of Mexico on the other. They smash into each other right over the peninsula. All that air has nowhere to go but straight up. And that daily pileup is exactly why Florida is the thunderstorm capital of the United States. All right, Our fourth and final mechanism works on a much smaller, more local scale. It's called localized convective lifting, and this one is powered directly by the sun. You've definitely felt this before without even thinking about it. On a sunny day, a black asphalt parking lot gets way, way hotter than a grassy park right next to it, right? Well, that extreme heat warms up the air right above the asphalt, making it less dense than the cooler air over the grass. So what happens? That pocket of hot air becomes buoyant, kind of like a hot air balloon, but without the balloon, and it just starts to rise. These rising pockets of warm air are called thermals, and they don't just create little puffy clouds. You know when you see a hawk or an eagle just circling way up high, not even flapping its wings? It's not magic. It's found a thermal. It's literally riding an invisible elevator of rising warm air to save energy. It's the exact same thing glider pilots use to stay in the air for hours. So there we have it. 4 totally different forces, all working to do one thing: overcome air's natural reluctance to rise. Each one creates clouds and weather in its own unique way. Let's wrap it all up. So let's bring it all home. We've got orographic lifting, where mountains force air up and create entire deserts. We've got frontal wedging, where warm and cold air masses collide to water our farmlands. Then there's convergence, that atmospheric pileup that gives Florida its daily storms. And finally, convective lifting, those little pockets of sun-heated air that let birds soar effortlessly. 4 completely different triggers, all solving the same exact problem, giving air that push it needs to get up into the sky. So here's my challenge to you. The next time you look up and see a cloud, don't just see a cloud. See the evidence of an invisible, powerful force at work. Ask yourself, which one is it? Is that cloud there because of a mountain range you can't see? Is it the result of a massive collision of air hundreds of miles away? Or is it just a pocket of warm air rising from a field down the road? The sky is telling a story, and now you know how to read it.